For problem number 6, we've got a solid conducting sphere and it carries a charge of positive Q, and the sphere is placed inside a conducting shell and that has no net charge. Derive an expression for the electric field in terms of distance. Let's start with the radius when it is less than the inner sphere. So this is going to be my Gaussian sphere, and I know that the sphere is a conductor, and we talked about how the electric field within a conductor is equal to 0. So that would be your final answer. The next one is when your charge is between A and B. So for this problem, we are going to have to use Gauss's law. So we've got EA is equal to Q enclosed over epsilon naught, and our Q enclosed is the charge of the sphere on the inside, which we stated was positive Q, and then our area is going to be the area of the surface area of a sphere, which is 4 pi r squared, and then capital Q for the enclosed charge, and in the end we get Q over 4 pi epsilon naught r squared, which is equal to KQ over r squared. So this is our answer for part 2. The next part, if we look up here, we've got, and let me use a different color, we've got B is less than R, R is greater than B, but less than C, so this is our electric field here. We're also told that the shell is a conductor, and so as we stated in part 1, our electric field in conductors is 0. Okay, so for part 4, we've got the last one where we've got a radius greater than the system of charged objects, and we're using the same kind of principle we've been using here, is that the EA is equal to enclosed charge, and they actually tell us that the shell is a neutral charge. It does not have a net charge, and so the only enclosed charge we really have is the charge of our inner sphere, which is Q, and we already established what the equation was for that from part 2, so our electric field is going to be the same as part 2. It's going to be KQ over R squared, and this should be squared right here. I missed that. All right, so for the next step, we are going to graph. We already know that the electric field is 0 when R is less than A, and when R is between B and C, and in between it has a inverse squared proportion. We can see here that our electric field, is proportional to inverse squared for both parts, and so that's going to be a function that for A it'll start decreasing, and then for C it'll decrease out to infinity. Same here, starts decreasing, trying to make them equal, and then decreases out to infinity. So that's what your electric field radius graph would look like. And then the charge on the inner surface of the shell, so I'm going to erase a lot of these dotted lines. What we want to look at is the fact that if we have a positive charge on our inner surface, the positive charges, and I'll just draw 4, are going to go to the outside of our shell because it's a conductor. And those positive charges are going to attract negative charges from the conducting shell above it. Even though it is neutral, it still has negative charges, but to make sure that it stays neutral, I have to equal the amount of positive charges, but those positive charges are going to go on the outer shell. So if I have 4 negatives on the inside, I have to add 4 negatives on the outside to make sure that this has a net charge of 0. So to answer the question, what is the charge on the inner surface of the shell? The charge is going to be negative because it attracts positive sphere on the center. What charge is on the outer surface? It is positive because it has to create a net charge equal to 0 on the shell. And then on the diagram below, sketch the electric field lines within a spherical volume of radius r is greater than c. So the electric field lines, when r is greater than c, is going to be the positive charges. As I drew them up here, I'm going to have positive charges, so it's going to be due to the positive charges that help neutralize the negative charges on the inside. So that would be your electric field, positive charges going out. And you can draw as many as you want, as long as it represents the equal charge on the inside. But that would be your final answer for part E.